Hello everybody, and welcome to the second part of LPIC 101.1 exam objectives. Just to recap, LPIC 101.1 exam objective is about configuring hardware. So in the first part, we looked at installing modules, uninstalling modules, and we looked at how buses communicate to the kernel to let it know that there's new hardware via interrupts, and then how the kernel, using the protocols of those various buses like USB and PCI, configure those devices. And they do this by communicating backwards and forwards about what the different resources are that need to be allocated. So the whole point of 101.1 is for you to be able to query and find out what resources have been allocated to devices, whether the device has been configured properly. Now remember, there's a whole bunch of different kinds of devices besides PCI and USB devices, which are the most common. You have, for example, hard disks or mass storage devices. We had a look at those, the different types: SSDs, SATA drives, and then also now the new NVMe protocol that's used as opposed to the SCSI protocol or SATA protocol to communicate to drives. We also had a look at the dev file system just briefly, or how items end up in the dev file system. Right? So they end up in the dev file system basically because the driver is responsible for giving them a label. That label will be something like dev SDA, and so the driver determines the naming of those devices. And what's important, what I want you to know for LPIC 101.1 is especially around the labeling of mass storage devices like USB drives, SATA drives, NVMe drives, etc. And we talked about how that is dynamic. It depends on the order in which they are detected on your system. So we also looked at disabling devices in the BIOS or UEFI firmware and by uninstalling modules. So now what we need to look up are the remaining key objectives or key knowledge areas in the 101.1 objectives. So let's quickly switch there and have a look at those. So if we look here, we'll see section 101.1, determine and configure hardware settings. So key knowledge areas: enable and disable integrated peripherals. We've looked at that. Differentiate between the various types of mass storage devices. We've looked at that. Determine hardware resources for devices. Now this we looked at maybe a little bit, but we're going to look at it more in detail. How do we determine the hardware resources? And the two main commands that I want you to know are lspci and lsusb. And we're going to have a look at how lspci and lsusb get information by looking at the sysf file system as well as the proc file system and the dev file system to get information that it displays to you in a human readable format. We'll then also talk about udev and how udev fits in. So udev is the userland tool that when a device gets inserted into your system and it gets configured, how userland gets informed that that device exists. And we're going to see how that udev works together with dbus to provide functionality for Linux desktop and Linux servers. Okay, so let's go and have a look at lspci again and run through that particular command. So I'm just going to switch to the terminal now so we can have a look at that. So in the terminal, this command we might be familiar with already, lspci. If we run lspci, we're just going to get a listing of the PCI devices on the system. Once again, how does this work? Well, the kernel is going to issue a command or protocol command onto the PCI bus and identify all of the devices that are on it. These devices communicate back, coming back with their vendor ID and product ID. The kernel then knows what driver to use or module to use to hand over to configure that device, and then it exports that information to userland. And so this is what we see in userland, right? What the device is. And if we put more V's for verbose, and you can maximum of 3, we're going to get more information about the particular device. So in this particular case, we can see this NVMe controller from Samsung, and it's using the kernel module NVMe to control it. And now we can see the resources that have been allocated to this particular controller. Now, if you want to see how this utility gets this information, we need to look at the proc and sys file systems. Now, one of the design principles of Unix is what's known as treat everything as a file, or the Unix philosophy as it's known, right? So that's one of the principles of the Unix philosophy, treat everything like a file. What does that mean? Just like you open and close and read and write to a text file, you use the same utilities and tools to open and close and read and write to hardware devices. As I said previously in part 1, it's not always a perfect abstraction. For example, a network card doesn't use abstraction, but as much as possible, Unix hardware attempts to use this particular abstraction to enable users to talk to and communicate with hardware through the kernel. So we're going to look at lsusb now as well, because it's very similar to lspci, and the principle is the same about how it gets the information that it has to display to the user once the command is run. So if you have a look at lsusb, it's going to be output in a different format, but it'll give us pretty much the same information, but except for the USB bus, right? So once again, we've got where the device is on the bus, who the vendor is, and what product code it is, and then the human readable name for that particular device. Just like with LSPCI, we can put a whole bunch of V's and get extra information, and this displays information, allocation information, and configuration information for USB devices. So where does LSPCI and LSUSB get its information from? Well, as I've been mentioning already, from the Proc and sys file systems. Now what's important to note about Proc, sys, and the dev file system, these are what are known as pseudo file systems. So what does a pseudo file system mean? It means if I was to take the disk out of this laptop, put it into another Linux box, and mount this disk, and then let's say I mount it under /mnt, and I went ls/mnt, there wouldn't be an ls/mnt/proc file system. It exists only in memory. Obviously, that Linux file system that Linux box that I'm using to mount this drive in will have its own /proc and /sys and /dev file system. So these are exported from the kernel, from kernel space to user land. So if you remember from part 1, we talked about kernel space because only the kernel has the privilege to access hardware directly and query it and configure it, whereas user space doesn't. So the only way user space can communicate with a piece of hardware is via the kernel, making calls to the kernel. And how this is achieved is the kernel exports information from the kernel space to user land to allow that. Besides, system calls it a user and application programming, etc. So proc and sys and dev are information has been exported, looks like files, to the user land so we can interrogate it and use user land tools to configure, interact with, and maybe even change some settings on our hardware. Let's start with LSProc. If we look at LSProc, proc short for process, we'll see there's two kinds of entities in here. One are directories, those are the ones in blue, and what is quite prominent are all the numbered directories. These are numbers for process IDs. Whenever a process starts in a Linux system, it gets assigned a process ID or a PID. And this is how you communicate and control and manage and monitor process in Linux. You always need the PID or the process ID of the process to be able to manage it. We'll look at that a little bit later. We'll look at process management. Now under this, under the directories that have PIDs or for processes, there's going to be a whole lot of information about those processes. For example, how much memory it's using, disk I/O, the command options that we use to start it, etc. We'll have a look at this when we look at process management. So what we're really interested in now is more of the files. So for example, if we have a look, there's CPU info. We have something like interrupts, I/O ports. Now these are all files which export information from kernel space about the various devices. So if we were to go cat proc CPU info, we'll get information about our CPU on the system. Now what it's going to list is that it's a genuine Intel R5, and we're going to see that this is a 4-core machine, processor 0. We scroll down all the way to processor 3, so there's 4 cores on this R5 CPU on this laptop. So if we have a look at I/O ports, we can see information about the I/O ports and how they've been assigned to the different drivers. Now, once again, this isn't very human readable, so this is why we use tools like LSPCI and LSUSB to interrogate this information. We can also have a look at interrupts, and let me just spell it right. What we can see here is the interrupt number, how many times it's been interrupted. So for example, interrupt 122 has been interrupted this many times, right, on core 3 of this particular system. This particular device driver here is for the USB bus. Okay, so that is what you really need to know about the proc file system. Now if we have a look at sys, it also exports information from the kernel, but in a much more structured way. So why are there two directories, proc and sys? Well, originally there was only proc, and a lot of device drivers and kernel modules started exporting data to proc, and it became a mess. So they decided to create a sys file system which is much more structured, so it's easy to find the information that you're looking for. However, some information still remains in the proc file system. So that is why there are two different file systems that essentially provide the same functionality. in terms of exporting data from the kernel. So if we have a look at sys, we are going to see that sys is far more structured. We have these top level drives, top level directories, and they divide up the information by the type of device, like a block driver, this bus for example, the class of the device, firmware, etc. Once again, for the exam, all you really need to know about the sys file system is it exports information from the kernel to user space, and it's a pseudo file system. But let's just have a little look here. If we go lspci, and we see that our NVMe controller is this particular hardware address, 03.00.0. So if I was to go lssys bus, now first of all we go list the buses on the system. We can see there's a USB bus, and we're also going to have a PCI bus. So we know this is a PCI device. So if I go PCI, I'm going to see information relating to the PCI devices, for example, device, drivers, etc. So let's go and have a look at devices. And what we're going to see here are the hardware addresses of these particular devices, where they're located on the actual PCI bus. And here we have our .03.00.0. So let's have a look at what's in that particular directory. And we can see there's a lot of files that are containing information that's exported from the kernel space. Once again, we can use simple utilities like cat to read these files if we have permissions. Let's, for example, have a look at the vendor ID, right, for this drive. We're going to see that it says OX144D. So this is the vendor ID that has been assigned to Samsung by the naming authority. So if you want to create PCI devices, you will go to the naming authority and apply for a number. They'll give you a number that uniquely identifies your organization. And then as you make products, you will assign product numbers to the different devices that you produce and manufacture. And this is what will be used to identify what driver or what module supports that device. Now the question becomes, since these are numbers, how come when we go LSPci, we see nice human readable names? Well, if we go -n, we'll see the raw information that's provided, because the computer obviously only deals with numbers, right? And at the bottom, we can see 144D, and then the product ID. Now, there has to be a way for the operating system to look up these numbers into human readable description. You have to have a way to resolve numbers to human readable format. So how does this work for PCI? Well, there's actually the text file that gets read to determine this. And if we have a look at this particular file, it's called PCI-IDS. So let's just list this particular file. There it is. And then let's list it to see what's inside it. Oops, must get my typing right here. So let's just have a look at this content of this particular file. So use less. And what we can see here is that we get the number that identifies the vendor, and then the vendor name, and then the products from that particular vendor. So let's have a look for our Samsung ID. Now we must bear in mind that Samsung also makes components that other manufacturers use in their devices. Same thing with Intel. So you might have a Dell laptop that uses an Intel chipset. So therefore you might find that Intel is referenced under a Dell vendor ID. So here we go, there's Samsung Electronics. In this particular case, it has got a vendor ID of 1099. Let's go in and search for our vendor ID that we are particularly interested in, which is 144D, and there we have it, right? Samsung Electronics Co. Limited, and we see all of the particular product IDs that Samsung manufactures. So what happens if you do a lookup and the vendor and product ID are not in this text file? Well, when you run LSPci, it won't be able to translate that into human readable format, so it'll just give you a number. You can update this file by running the command update PCIDs or PCIDs, and this particular file gets run automatically via cron job or a scheduled job in your Linux file system. So if I'm going to go sudo and run this, it'll ask for my password, and it'll go off and update this particular file. So if you have if you do LSPCI and it comes up with a number, you can run sudo update PCIDs and it might translate it for you into human readable format. Of course, this normally doesn't solve the problem because it means that your kernel doesn't have the driver for it. And you might have to upgrade your system or update it to the next version, or at least upgrade your kernel to be able to get support for that particular device. So typically it's a bad sign for your LSPCI. You've got this piece of hardware, you've plugged it into the machine and it doesn't seem to detect it and it's not working, and you've got LSPCI showing a number. Well, then it means you probably don't have a driver for it. This doesn't happen that often or at all these days, except maybe in embedded devices when you're using something that's pretty cutting edge. Or you're using a periodic distribution like Ubuntu and you're using 16.04 and it's now October 2017, something like that, and this device came out in October 2017, so Ubuntu 16.04 might not have that particular driver in it. Okay, so let's quickly have a look at the dev file system, because we have looked at this before and we described how entries are made in the dev file system. Typically this is by the kernel module that's responsible for configuring that particular device. It is going to create an entry under the dev file system for us. Right. So most common ones we have talked about are things like for your SDA, for your mass storage devices, when you plug in a USB stick, etc. One thing to also know, if you run the command ls-l, this stands for just give us a long listing, information about the files that we have under the dev file system. So for examples, it gives us the owner of the file, the group that this file belongs to. This is known as the file, the driver ID, right, that identifies internally the driver has a way of numbering and enumerating the various devices, because there might be more than one hard disk, one USB device, etc. And then we obviously have the actual label for that particular device. What's important here though really is the permissions on this device, because of the Unix philosophy, which says treat everything like a file. And remember, as we said, we can just read and write to a file using our normal utilities that we read and write to a text file. We have permissions, and they're grouped into three. The first one over here is for the owner, that in this case is root, read, write, and this should be execute, but there's no executable permissions on this particular device. Read and write without execute permissions for the group, and then other or global has no permissions on this particular device. Don't worry too much about the permissions. We're going to talk about that in a lot more detail when we look at file system permissions in another objective. But the key thing that I want you to know about for the dev file system is that character devices start with a C. Now normal devices, if you go ls-l, have a dash in front and a D for directory. So character devices are devices that get read one character at a time, like keyboard input or the mouse movement, etc. Block devices are devices that get read in blocks of data. So for example, when you read from your mass storage device, it's not going to read a character at a time, it's going to read a block of information from the drive and then send it through to the kernel, and these are known as block devices. So yeah, for example, on my NVMe device, we can see the B for block device. Now, one thing that's also important to understand about the dev file system, it also works together with udev. So udev, as we talked about, is a user space service that listens for events relating to hardware and then takes particular action that can be defined by the system administrator when a device is detected or removed. So udev then talks and communicates also with a software bus called the dbus or desktop bus. And this is the way that applications and user space communicate to each other, pass information or messages backwards and forwards between each other. So for example, if you insert a USB stick that's got photos on it, how does it know that it must open up the photo app to start showing the photos? Right? So there's a whole sequence of events that has to happen, from the USB bus signaling to the kernel that hey, there's a new device. The kernel then loads the module, that module then configures the device, udev gets informed, udev then uses in this particular case something called udeskd, which will then tell the operating system that hey, or the desktop manager, that guess what, by putting a message on dbus that there is a new device, mass storage device, and then using the rules it will decide what to open, whether it opens a file explorer or maybe opens a photo editor or a photo viewing app. So that's just a brief overview of the sequence of events that occur when a device is plugged in, and all these components work together so Linux can provide the user with a seamless experience of using hardware such as USB devices. So just to illustrate and demonstrate the Unix philosophy of treating everything like a file, I'm going to now look at how we can not only read from files for information that's been exported from the kernel to user them, but how we can also write to them. So just to demonstrate the principle of treat everything like a file, which is part of the Unix philosophy, we're now going to use one of the files under the Proc file system that enables or disables IP forwarding, and we're going to see how we can actually change configuration by writing to that file. Just quickly, what is IPv forwarding? Well, if a packet arrives to your network card and it's got an IP address that isn't for your network card, is your machine allowed to forward that packet on to that particular IP address that it is destined for? So this might be the case for a router where it knows about IP addresses behind the router, so information arrives, a network packet arrives, it's not destined for the router itself, but it's sent to the router because the actual target IP address is behind the router. Then the router can forward that, often usually doing some firewall inspection, the router can forward that to the destination IP address behind the router. That's known as forwarding. So typically, a workstation shouldn't be forwarding packets. At least that was back in the day. Now with virtualization, containers, etc., there's a lot of packet forwarding going on, so normally it's turned on by default. But we're just going to turn it off so I can show you how to write to a particular configuration file under Proc, and then how this will change how the kernel behaves. So just to prove to you that you can read and write to these files. So let's have a look at that. So if we have a look at the file, it's under the Proc file system, and it's called procs under the procsys net IPv4 IPv forward. So it's just a normal file. If I go ls-l, it looks like a file, right, with the read-write permissions. And if I say cat, now I can read this file. And we can see here in this particular case that IPv forward is disabled. So if I want to enable IPv forwarding, how do I do it? Well, I just write to the file. Now, because of permissions on files, only somebody, the root user, can change configuration. So therefore, we're going to have to use a command which is echo 0, which means, let's make it actually echo 1 to turn it on. 0 turns it off. So we're going to say echo 0, which echo just means write to the console. But then we have this pipe character, which we'll explain in more detail later, which takes the output from the first command and makes it input to the second command. And we send it through to this command called T, which we're running as a root user using sudo. Now T is a command which does two things. It's like T as in the letter T. It will write the output to standard out, which is the console, and it'll also write it to a file that we provide. In this particular case, I'm saying write it to the procsys net IPv4 IPv4. So if I run that, and now if I go cat, I can see that this value has changed. So this machine will now be able to forward packets to virtual machines that are running on it, or if it was dual honed and it knew about other IP addresses or other machines behind it that the arriving packet couldn't reach, it would then route it to those particular machines. Okay, so let's have a quick look at where we are in terms of the objectives. So we have got a conceptual understanding now of syslus, udev, and dbus. We've looked at tools and utilities. We looked at tools and utilities to manipulate USB devices. And we looked at tools and utilities to list various hardware information. We know about the sys file system, the proc and dev file system, modprobe, lsmod, lspci, and lsusb. So that's it for this lesson. We at least covered now in two parts, 101.1. We did spend much more time than the weight of 2 that is required for the exam on this, but I like to provide the background so you actually understand why these things work the way they do. Next, we'll move on to 101.2, boot the system. This has a bit more of a weighting of 3. Look forward to our next episode dealing with 101.2. Thank you.